Hello, everybody. This is Aaron Schwartz, one of the secondary math specialists for MCPS. Today, we're going to look at a video called Making a Point, or Point Slope Derived from Patterns. In Unit 2, Topic 2, students learn to build equations recursively and explicitly as descriptions of recurring patterns. Equations can be used as succinct descriptions of a pattern. Some of the helpful skills that students have already learned. Students have already learned proportional reasoning with integers and rational numbers. This has been done in Math 6, Math 7, or IM. They've also learned that coefficients of a number represent the number of addends of that number. This is done in elementary school and Math 6. Numbers can be decomposed to reveal patterns. This is done in elementary school and is very important for developing an understanding of point-slope form. Take a look at this table. We have a typical table of values for x and y. If you've already seen the videos for growing dots, both the linear and exponential, much of this is going to be very similar. The difference will be that we're not starting at 1 or 0, but we're starting at an arbitrary domain value. In this case, 10. One of the first things I would ask students to do is to complete the table for the domain values 13 and 14. Students may readily see that we're increasing by 3 each time. If they can do that, we have enough to go on and develop the patterns that they need. Just as in the growing dots videos, we're going to decompose those range values. We're going to decompose them in terms of our initial range value, 4. 4 decomposes to just 4. 7 is 4 plus 3. And so on through our table. The next thing we're going to do is expand the table again to show the pattern of the addends that we're using. Initially, we just have 4, and we're increasing it by no addends of 3. Then we increase it by one addend of 3, and so on. Just as in previous videos, we now want students to make a connection between the number of addends and the value of x. When x is 10, we have no addends. When x is 11, we have one addend. When x is 12, we have two addends, and so on. Now we want to get students to express what the connection is. They may readily see that whatever is inside the parentheses is always 10 less than whatever the value of x is. The goal is to get students to express this in terms of an algebraic expression. Since 10 less indicates a deduction of 10, it's x minus 10, and we can complete the equation around it. Just as in the growing dots one, let's draw some attention to some key details. Notice that the values for x and y, our initial values of 10 and 4, appear in the expression. This is really critical. The value of x is whatever is subtracted from x inside the parenthetical expression. The initial value of y is whatever our constant will be. From here, we can actually develop a rule. For any value of y, it's equal to the slope times the quantity x minus our initial x value, and then increased by our initial y value. Or y minus y1 equals m times the quantity x minus x1. Let's do it again. This time we're going to start with a negative domain value and see if the pattern holds up. We have a table that's increasing by 7, and we'd ask students to complete the table. We're going to expand the table just as before. We'll start with 14, 14 plus 7, 14 plus 7 plus 7, and so on. Now we're going to redo this as a pattern. 14 plus no products of 7, 14 plus 1 product of 7, and so on. Now we want students to make a conjecture or a hypothesis about the connection between the values of x and the values of inside the parentheses. At -7, it was 0. At -6, it was 1. At -5, it was 2. At -4, it was 3. There are two different ways that students may perceive this. They may perceive the number in the parentheses as 7 more than whatever the value of x is. They may also say something like, well, we've taken away -7. Both of these are very important perspectives on what's happened and need to be included in the classroom discussion. We're going to start with x plus 7, the idea that whatever the parentheses is 7 more than the value of x. And we'll build our equation around it. Now, in the previous example, we subtracted the initial value from the domain. So you know what? Let's do the same thing again. Let's rewrite the positive, but this time we're going to rewrite this expression by deducting that initial value. 7 times the quantity, x minus -7 plus 14. Our integer operations let us know that those two expressions are actually equivalent. Notice again that our initial domain value ended up inside the parentheses, and our initial range value was the constant added outside the parentheses. The rule that we developed before holds up. So some typical tasks. Write an equation for a line with a slope of -2/3 and passing through the point 5, 6. This used to be a very high-level task, or was often perceived as a high-level task, because we expected students to figure out the y-intercept and do an enormous number of calculations in order to solve this particular prompt. But in actuality, writing the equation for this is very simple once you know point-slope form, because we have our point and we have our slope. We can just substitute in. A slightly, and I emphasize slightly, more rigorous task is when we have to write the equation of a line passing through two given points. All we have to do is determine the slope, and then just pick one of the points and write the equation. The slope is 9/5, and we just have to pick a point. I'm going to pick -311. I know that I'm going to subtract a -3, which is the same thing as +3. So y equals 9/5 times the quantity, x plus 3 plus 11. We're going to go ahead and we're going to open up a Desmos exploration in the next part of the video. I'm going to go ahead into Desmos. And I'm going to open up a graph that I've already made for this video. We're looking at point slope form. This is a graph easily developed by any teacher. There will also be a link to it in our MyMCPS classroom. Notice that I have sliders built for M, H, and K. I've substituted H for X1 and K for Y1. And I've done this because it makes point slope form mirror the vertex form of a quadratic. I've also set it up so that it will display the equations and the point on the graph dynamically as we change the values. Let's go ahead and start moving h around and seeing what happens. Notice that as I move h around, I have this horizontal change. As I go to the left and right, I can see the values in the equation and the line changing. One of the other key things that I can see is that as I go to the negatives, I have x minus 4.1. Again, confirming that we can just subtract whatever the value of that point is. Now let's take a look at k. As I move just k around, I again see a vertical movement, a vertical translation, and the equation changing. And I can make conclusions about how h and k change this line. I'm going to go ahead and move this line down a little bit, and move it closer to the origin. Notice them not exactly on the origin. The next thing that I want to do, I actually want to start playing around with slope. One of the things that I can observe is that slope becomes a rotational value about the point that I've named in my equation. I can ask all sorts of extension questions from here. For one thing, if I've given you a point, does the slope impact where that line is centered on your coordinate plane? And the answer is obviously no. But students can explore this by playing around with the Desmos exploration. It makes for a very powerful experience and a better precursor to skills that will be developed later when we get to quadratics and to Unit 5. I hope that this video helps teachers create classrooms where students explore math, observe patterns, and develop conceptual understanding. If you have questions, comments, or have a video idea, please email me at the address below. Thank you. Have a nice